Can you see this PPT?
Yes, sir.
So in continuation with
Yes.
yesterday's, hello, shall I start? So I hope you can see this. You can interrupt me anytime if you don't see this or there is some problem. So yesterday we saw this ID3 algorithm, and then we saw that how information gain for an attribute uh, can be used as a measure to split the table to smaller pieces, and then we can further split it so that a pure and pure form of data is achieved, and that's the logic behind ID3. So information gain matrix used in ID3 always positive or zero. So it is always positive value because information is always gained. So as we go towards purity, so we always gain some information. On the other hand, when a training set is such that if there are k classes and the entropy of training set takes the largest value, that is log base 2k, uh, then information gain will be zero. So this occurs when the classes are balanced. So when you face balanced classes, even after splitting, you get the same balance, then information gain becomes zero. Say for example here, we have this set, say 1, 2, 3, 4, 5, 6, 7, 8 samples are there. So if I split using X variable or X attribute, I have three values here, I think, yeah. So if I split using this, uh, there are four values. So I have four values here and two classes A and B. So I get four to this side and four to this side. So the ratio is again 50-50. So there is no gain. Here also I have 50-50 samples. Now if I use Y feature, the Y feature can take two values, 1 and 2, and there are again two classes like this. So we have samples again 50-50. So when I divide with the help of X, I get same ratio as parent ratio, as well as for Y I get same ratio as parent ratio. So the combining effect entropy of these two is same as of the parents. So my gain is zero in this case. So you can check with this formula of entropy. If such things are happening, then what is the value of gain? Now the thing is that if you have continuous attributes, what to do? So in case of the previous data set, we were having discrete values, so things were simple. We could have just taken one by one all the levels and then we could have done this splitting, or we did that thing. But now if my attributes themselves are continuous, what to do? Say for example, I have some height as attribute in my table, then it can take any value, maybe 6 0.3 or maybe 1.2, maybe 2.4. So this can take any value. This is a real valued variable along with some other data which is discrete valued. Then what to do? How to split the table? So what we can do is discretize the feature which is continuous. So we can break this. Suppose this is height some 0 to 7 feet. I can break in some ranges like this. Okay, so and my table I can discretize. Say I can say 0 to 1 as suppose 1 and 1 to 2 as 2, and like that I can give some labels, and then I can split my table with the help of these numbers. Okay, so I can put some threshold, maybe say greater than 0, greater than 1, greater than 3, less than 4, like that I can keep on checking uh, the values, and then I can uh, divide the table. Okay, so what I want to say is, suppose this is my complete table D, and there is some height as my variable, and that I will divide this into say 0 to 1, 1 to 2, and like that. So I have say 7 such sections. Then I can take one by one all the values and then decide what value I should use for splitting the table. Okay, so we will see one example and maybe later how to do this. But timing, remember that uh, we can do like this. If you face some continuous features, we will do this. So when you use ready-made packages available in Python, say sklearn, and so this they will do this automatically for you. You did not worry about how to divide a continuous variable. We will see one example today how it is doing it automatically. So it will check for the range and then it will start splitting it as per the requirement. The other approach we can have is we can sort all the values which are all the values of say height that are appearing in my table. Say this is height attribute. You collect all the values which are appearing and sort them. Okay, sort in say this way, lowest to highest. Then you take the midpoints of these values. Say this value is suppose 1 and this is 2.2 suppose. Then you take 1 plus 2.2 divided by 2. Okay, so 3.2 by 2 will be your threshold for splitting the table. You can check for all such possible things and then you see what value you can use for splitting the table. So it may look tedious, but it will be done fast within those packages. You can uh, try with your own. I will give you the commands how to do this. Now this is the sklearn package command. So you can uh, download this in your Python Anaconda, you can say, base, and then you can use it. So you will require these two packages, matplotlib for plotting the graphs, and you can directly load the available data set. I will give you one example how to load externally also. I think we have even done that in regression using pandas, but here uh, it's within the sklearn package. So this is a very famous dataset, iris dataset. You just say load it, so it will give you two things. One is the target value y, and the other one is feature vectors. Okay, so that will be given to you. You have to just pass this thing to the command decision tree classifier. So this will be making instantiation of this command or this object, and you will pass on this X and Y directly to this fit command, which will immediately fit the data and display you this tree. The command for displaying the tree is tree.plot. So it's very simple. Hardly 3-4 commands are required to implement what we have seen, because it's ready-made. We can just use it. Now this is the uh, tree constructed for iris dataset. So iris dataset is consisting of 4 features, and fifth one is your target value or class value. So there are 3 classes, say 1, 2, and 3. Okay. So that way it's very small, around 125 or 124 samples only. So you can see that, and remember all these are continuous valued attributes. Now you can see the first root is with the fourth so feature. Here feature numbers are from x0 to x3. That means there are 4 features. So it is checking for x3 whether it is less than or equal to 0.8. If yes, then straightway it will throw you to class number 1, omega 1. Okay, so immediately you will be declared as omega 1. Other features are not required for the uh, comparison, because when it compares with this value 0.8, you will see that 50 samples. Okay, I think there are 150, right? There are 150 samples in iris. So 50 of them, they belong to omega 1, and all of them are here. Okay, so this node which represents omega 1 is pure node. No other element from other classes are here. So this is the purest node. So entropy here is 0. Okay, entropy becomes 0. Entropy at the beginning of the table was 1.585. Now when you say yes, then you will be reaching to this node. When you say no, you are here. Now here you check, or this table will check x3 whether it is less than 1.75. If yes, then it will go to this side. If no, then it will go to this side. Okay, like that it will go on and on. Now here at this level, you will see that there are 50 samples from omega 2 and 50 samples from omega 3. So there is a mixture of these two uh, classes. So this is not a pure node. So this will not be declared as a leaf node. Okay, so when you extend your split, it is now done with the help of x2 here, and still you will find that it is not a pure thing. It is one with omega 2 and one sample with 45 samples with omega 3. So you keep on dividing your table till you reach the pure node. Say here you will see that one sample is there, but it is belonging to omega 2, 2 samples with omega 3, like that. Okay. So this is done automatically. Suppose I want to check for certain input, new input like this. Say this is my new input vector, say 2211. I want to check what to which class it belongs. Then I will use clf.predict. So predict is the function to which you will pass this x test. Okay, so x test is passed to this. It is declaring it as omega 0. In this case, it means omega 1. Okay, so Python starts with 0 to 3, in 0 to 2 in this case. Okay, because there are three classes. Now you can use a predict probability command which gives you the probability of occurrence of this particular class. So instead of just assigning you a class, it will give in terms of probability in different classes. So what is probability here, here, and here? So this is omega 1, omega 2, and omega 3. Now here it is fully belonging to omega 1. Now if I go with some more test, say like 2252, then I am declared as omega 3. The probability here is again in omega 3 it is 1. For others it is 0. You can see that sum of this will be 1. Now if you want to check, how this is declared, you can check with this example. Suppose I choose this one 2211. So this is x0. This is just 1 second. 0, 1, 2, and 3. Now initially I'm checking for x3 whether it is less than 0.8. So x3 is in this case not greater than point is actually greater than 0.8. So I will be moving this side. Okay. Then I'm checking for whether x3 is less than 1.75. Then it is yes. Okay. Like that I have to track what is happening in my table. And finally I will land node, leaf node, which will be declaring you or giving you the class. Okay. Now the next algorithm is called as CART, or classification and regression tree, which is very similar to ID3, and these two algorithms actually came into existence in the same year. Okay, I think in 84 or so. So it is observed that information gain measure used in ID3 is biased towards test with many outcomes. That is, it prefers to select attributes having large number of values. Okay, so that is the observation in ID3, that it will try to select the attribute for splitting which has large number of values. And in ID, in CART, the basic thing is, or basic difference is, CART is strictly a binary decision tree. Now, even though I'm showing you this diagram for ID3, as such, this is the diagram of CART only. Okay, CART is implementing only 2 splits at a node. So this third one is not allowed in CART. Okay, remember, in ID3, you can split with 3 values, maybe 4 values if you have, that is allowed. But in CART, you have just only 2 splits for a node. You may have 3 values for a feature, but you can split only into 2 branches at a time. Now how it is done, we will see. Now CART generates only binary tree. This is the main difference. And ID3 uses information gain as a measure of splitting, whereas CART uses this Gini index diversity. So how it is being split is also a difference, and there is a difference in splitting the table. So two sections, any value. Now the base of this Gini index is the variance between these classes and probability of actually the classes. Now what is done actually is, if you have multiple classes, so you can have this formula, that is probability of omega I into probability of omega j. So this, if you want to do for many classes, okay, let us take j equal to, say, I is not equal to j, and we have suppose 3 classes. So we will have probability of omega 1 into probability of omega 2 plus probability of omega 1 into probability of omega 3 plus probability of omega 2 into probability of omega 3. Like this we can have this variances. Now instead of doing this way, we can calculate this easily instead of this, using this formula, where I will do this 1 minus probability of omega 1 square plus omega 2 square plus omega 3 square. So this thing and my earlier description, they are same. Okay, so this is a simpler version to calculate. Instead of calculating so many multiplications and all those things, we can do the same calculation with this. So the basic thing is, you can just remember, instead of remembering everything, you just remember this is based on something called as variance, and you just take the square of the probability of individual classes, add together and subtract from 1. That will give you a Gini index. So here it is describing you what is PI. PI stands for number of samples of, say, ith class in this data set D. Suppose data set D consists of 100 samples, and out of that 30 samples belong to class 1, then probability of class 1 is 0.3. Now if you see or compare the entropy, Gini index and classification error, this is the diagram for two class problem. You can see entropy is 0 when probability is 0. Suppose I have omega 1 and omega 2, two classes only. Now probability of, suppose omega 1 is 0, means what? All the samples given to you are belonging to omega 2. That's why the probability of omega 1 is 0. So everything is omega 2, then there is no entropy. There is no uncertainty. Everything is certain. That means you can simply blindly say that everything belongs to me is omega 2. So entropy here is 0. Similarly, when you say all the samples belong to me are omega 1, so probability of omega 1 are probability of omega 1 is 1, then still there won't be any uncertainty, so entropy is again 0. So entropy becomes 0 in both the extreme cases, and entropy is highest when you have 50% omega 1 and 50% omega 2. So if that is the case, then you get the highest entropy equal to 1. Okay. Now what happens if I use, instead of this, Gini index? So Gini index is giving you 0.5 as the highest value. Now why it is 0.5? You can see here, if I have only two classes. So this will be point 0.5 and 0.5 probability for two classes. So 0.5 square is 0.25 plus 0.25. Okay, so this becomes 0.5. So this summation is 0.5. So 1 minus 0.5 is 0.5. So the maximum value for Guinea is 0.5. The shape will again be same. Now for omega 1 equal to 0 probability, again Guinea index is 0. Again for uh, omega 1 equal to 1 probability, again Guinea index is 0. Guinea index is 0. Okay, so this index actually resembles to this entropy, but calculation is very simple. So that's why it's very popular. And even in this sklearn package, the default index is Guinea. So if you do not specify, it will use Guinea. If you want to specify or use entropy, then you have to specially tell that use entropy for this. Okay. Now otherwise it will use Guinea. Now this is the third graph, is the misclassification graph. So instead of using these two, we can even use misclassification graph or misclassification index. Now what is misclassification or misclassification error? Say it's like in Bayes we did it, say 1 minus max of probability for all the classes, because we are sticking to max probability for our decision. Say I have omega 1, omega 2, omega 3, and this is suppose 0.5, this is 0.3 and 0.2. Then what is our decision? Our decision is 0.5. Go with this max. So how much error I am doing when I take this decision? So I do have error 0.5. So even I can use this as my splitting criteria. So that is called as classification error criteria. So if you do that, then your graph is this triangle. Okay. Now, if I do this rescaling or just multiply these two curves by 2 so that it looks very similar to entropy, you will see this graph. Okay, so it's Guinea multiplied by 2 and this misclassification error is multiplied by 2. So these are three graphs. Now this Guinea criteria is much faster because it is less computationally expensive. On the other hand, the obtained results using entropy are slightly better. Nevertheless, the results are so similar, it does not seem to be worth to use this entropy as a measure. Okay, you can just stick to Guinea, which is simpler. Now, why we do not, as I said earlier also, we do not generally use classification error as the measure in decision trees. Instead of that, we use entropy or Guinea. Now we can take one example. Suppose this is a binary feature, say x1, x2, and x3. We have three binary features in our table. Okay, and we have one sec. There are two categories, say 1 and 2. Now initially, this first thing shows that we have 80 plus 40. That is total samples with me are 120 with say y equal to 1 or category equal to 1. Uh, we have 40 samples. and for y equal to 0, so I should say here I think y, and I can take values 0 or 1. Okay, so if I have uh, initially there are 120 samples, out of that 40 outcome is y equal to 1 and 80 outcome is y equal to 0. Now the first feature, suppose I use x1 equal to 1, whether x1 is 1 or not. We have only two values of x1. Say x1 is a binary feature, so it can take suppose 1 or 0. Now I check whether x1 is equal to 1, then I say yes. Then I go to this side and I have another split of 12 samples here and 38 samples here. Then I use x3 as my feature, then I get this division. To left hand side, when I say no, I have 28 and 42 as my split. Then this is further divided into 28 and 42 with the help of x2. Now let us consider the binary tree starting with training samples 40 positive and say 80 negative, or with y equal to 0. Further, let us assume that it is possible to come up with 3 splitting criteria based on 3 binary features. Now if I use classification error as my measure of splitting, now see what happens. So initially, what is error? So when you have a mixture of this 40 plus 80, 120 samples. So what is majority? Majority is 80, so your decision is always the class of 80. So 40 is your error in doing so. Since you are declaring everything as of the class of 80, this 40 will be misclassified. So what is misclassification error? Is equal to 40 by 120. So this is the error at the top. Okay, you can see this is the measure here and error here at the top. Now when you split this, you have now 28 and 42 as your split in left hand side, and on the right hand side it is 12 and 38. So how much is misclassification? Out of these 70 samples, you have the minority, that is 28 misclassified, and here out of 50 samples on the right hand side, 12 are misclassified, right? So this is the error on both sides. Now the combiningly, the effective error at this level is nothing but this much, this weighted average. What it means? So you have 70 samples out of 120 here multiplied by this error, that is 28 by 70 plus. Now go to this side. How many samples are there? There are 50 samples out of 120, that is the parent count. And what is error? It is 12 by 50. So this you compute is the weighted average misclassification error. Now you will check that when you do this calculation, you will see that the this gain is actually 0. The error here, the weighted average error at the second level, weighted average error at this level is same as the parent error. Okay, it is same. So what is gain in doing this split? Gain is 0. Okay, so that is why the algorithm will stop here. When there is no gain, it will think that we have to stop. So that's why we cannot use misclassification error. I hope the idea is clear. So why we cannot use? Because the stopping criteria in ID3 or in CART is that when there is no gain, you stop and declare it as a leaf. Okay, so your algorithm immediately terminates since there is no gain. But that is not the case. So instead of that, suppose I use entropy on the same problem, same division, and I calculate entropy. Now see, the parent entropy here is 0.918. To left hand side, after splitting, entropy is 0.971. Entropy on right hand side is 0.795. Now if I calculate gain, so this is the weighted average entropy at second level. Now how it is calculated? It is calculated in same way. So what I do? I take this 70 samples on the left hand side divided by 120 into the entropy value here is 0.971 plus I take right hand side, there are 50 samples out of 120 into the entropy value is 0.795. So if I do this addition, it will give me the weighted average entropy at this level. Now I subtract from the parent value, so it gives me 0.02 as the gain. So gain is not 0 in this case, there is some gain. So the algorithm will split this table like this and then it will try to split further. So algorithm will not terminate at this point. Now why this has happened? That is the main thing. In the earlier case, my algorithm would have terminated here itself. Since there is no gain, I will just stop. Now when I say that I will stop, note that I am assuming that if I use x1, there is no gain. If I use x2, there is no gain. If I use x3, there is no gain. If this is the case, then only it will terminate. Now assuming that it terminates like this. Now but with the same split, if I use entropy, this is not going to happen. Now reason is, if I zoom this graph, the green square shapes are the entropy values for probability, that is 28 by 70 and 12 by 50 of the first two child nodes in the decision tree. Okay, so you can see the entropy figures here, they are here. And this is the position of actual parent entropy on this entropy graph. So this is entropy graph. This was the parent entropy at the beginning. So when I split using suppose x1, then there are two things, two parts of my table with these two entropies. Now when I take the weighted average of these two, the weighted average of these two will lie here. Okay, weighted average of these two children is here. Now parent is here. So the difference between these two is called as gain. So there exists some gain. That's why the algorithm will continue. Now if I use misclassification and say it will be something like this, some graph like this of misclassification, and maybe this is the error for left hand side, maybe this is the error for right hand side, and if I take average of these two, it will be somewhere here, and for parent also it will be here itself. So there you will see that there is no gain. Now since I have this curve here, a bell-shaped curve, there will be always some difference in parent and children. There will be some gain. That's why our algorithm will try to continue. So this bell shape is important so as to continue the algorithm. That is the only reason people use this entropy or Gini as the measure of splitting instead of misclassification. So misclassification may terminate your process very early without actually splitting the things properly. So the similar to our IG information gain in ID3, here we use Gini index diversity. So what is Gini index diversity? We find out, so this is my parent table or parent node, then I make two children, say D1 and D2. So I calculate Gini index at the parent site, and then I find out Gini here, and then I calculate the average Gini value for the children. So that is say GD using some attribute A, and this I will subtract from the parent. So this is called as Gini index diversity. Similar as of the previous case. So earlier here we used to have entropy of parent and entropy of children. Now instead of that we are using Gini index of parent and Gini index of children. Now similar to the earlier, we use the discrete valued feature for binary splitting. But here the problem is, if discrete valued feature has many values like A1, A2, up to AM, then since we just split the things into two halves or two branches, we may find difficult. Now, how it is solved? Suppose I have this many features, this many values of a feature A. A can take these values. So in total, there are 2 to the power m, say, combinations of this A1 to AM. Now out of that, the all empty and all present, these two things are useless. So we will subtract from that. So 2 to the power m minus 2 possible ways of partitioning this data set. You can imagine I have attribute A which can take A1 to AM different values, A1, A2 like that up to AM different values. Then we have 2 to the power m minus 2 possible ways of splitting. Okay, so how to do this? So what we do, we take the, suppose AM or A1 as the criteria. Anything equals to AM will be this side, no will be other side. So here suppose I am saying if attribute value is certain AM or A1, then if it is answer is yes, go to this side. So this table is with value A1. and this side is other than A1. Okay, so like that you may have more conditions here. So this SA is a set of attributes. So I can say A1 and A2. Then the question becomes, if A is equal to A1 and A2, then go this side. So this is combination. So like that we can frame 2 to the power m minus 2 questions at this node to split using attribute A. Okay, so you can see the complexity at the first stage itself when we have multi-valued function or multi-valued attribute. Now if you have continuous valued attribute, then we have to again form this discretization, same as earlier. You just take all the real values, sort them, and you can take middle values of these values as the splitting criteria, and then you try to split like this. A is less than certain value, then go this side. No, then go this side. Now suppose we take this example of some employment data. So this is some employment data. So this age attribute is taking three values, salary is taking three values, job is taking two values, performance is taking two values, and the outcome class, there are two values. Now if I use the Gini index of and calculate the Gini index of this table, you will see that there are 9 samples belonging to, say, this 1, 2, 3, 4, 5 to no, 5 to no, and 9 samples to yes. Okay, so 9 by 14, out of 14, 9 are yes and 5 are no. So 9 by 14 square plus 5 by 14 square, this is the probability of yes, and this is probability of no. So make it square, add and subtract from 1. That's it. So this will give you 0.495 as the entropy, sorry, not entropy, it's a Gini index of parent table. Now we have to divide this table using 3 attributes. 3, rather 4 actually. There are 4 attributes. So this number is just a number of the sample. So this is not an attribute. So there are 4 attributes. So based on this, we will divide this table in tomorrow's class. So don't miss tomorrow's class. We will do this splitting based on Gini index.
तुझ्या चुकीनं झालं. काय चुकलं? ते तर आपली ऍडव्हान्स झाली तरी ते काही झाली नाही. मायनस प्लस प्लस मायनस. ठीक आहे.